All right. Hello. Hi. Okay. Yeah, there was some confusion. There is lab tomorrow as per usual, as per the syllabus. It doesn't say that there are 10 labs. It says that the labs are worth 10 points. So there is a lab tomorrow. You paid for it, so you're getting it. So all right, it's hopefully gonna be fun. So what I want to do today is I want to go a little bit further into the game stuff, just to wrap it up. And we'll then do kind of a mix of prepare. Oh, I have a thing. Okay. So, yeah, by the way, that's like U of T mathematics. It's trivial. It's like U of T math sweatshirt someone made. All right. So we're gonna do kind of a mix of preparing for the lab and setting up for one of the final kind of interesting recursion examples. So, all right. So first, we are gonna do the game again very quickly. So the game was raised to 21. If you weren't here, the game is like this. So we start with 0, and then the moves are +1 or +2. Hello. And each player gets to either say +1 or +2. The first person who gets to 21 wins. So the game might go like this. So 0, and then you say either +1 or +2. Maybe you say +1, and maybe the other person says +2, and then maybe you say +2, and maybe the other person says +1, and then maybe you say +2, and so on. And whoever gets to 21 first wins. And what we did was we wrote a function that says if you get to something like 6, are you guaranteed to win if you don't mess up or not? So that was the function. So we called it isWin. And the idea was we return true if getting to n means guaranteed win with perfect play. And it was really easy because if you are at the target, that means that the answer is true. So like if you go to get to 21, that means you're guaranteed win because you just won. So we just said the base case is if n is 21, then we return true. And then for the recursive step, the logic was, well, I win if my opponent loses. My opponent loses if whatever they do, they cannot win. So we try every possible move. So we'll say, okay, so if my opponent wins with n plus move, then I lose. If I tried every possible hypothetical move for my opponent and it did not turn out that they win, that means that I win. So I return true. All right. So the logic here is if my opponent can win, and the way I determine that they can win is I just call isWin as a helper function. So I'm assuming that this win works. So I check every possible move by my opponent. If my opponent can win, then I lose. If my opponent cannot win, whatever they try, then I win, so I return true. So that's the logic, right? And again, like I said, you can do this with anything. So you can do this with tic-tac-toe, right? So here, what we did is we basically created n plus move. So in the same way, in tic-tac-toe, you could create a position that your opponent would create and check, does that lead to a win? Right? So this kind of structure, in principle, can work in anything. It can work in chess. It can work in Gomoku. It can work in tic-tac-toe. The problem, of course, is that it will not in practice work in Gomoku. It would be too slow because there is too many possibilities to map out. But eventually it would work. Eventually it would return if you do something like that. Again, 2015 exam, last question, I believe, is the setup for tic-tac-toe if you want to practice this. Okay. So, all right. So that's is win. So what I wanted to do is just write a thing that actually plays. So what you're going to do is we're going to say, okay, so we start with current position being 0, and the same way we did with tic-tac-toe. So we'll repeatedly ask the user for a move and we'll make a move ourselves, right? So I'll say so if we're not done, the user's turn is false initially. So if it's not user's turn, then it's the computer's turn. So what do I got to do? I got to say, all right, I'll try every possible move to see if I can win, right? If I can win with that move, I'll make that move. If not, I'll just do something, right? So I'll say, okay, moves is 1, 2, and I'll say, okay, for move in moves, if I can win using this move, then that is what I'll do. Right? Sorry, move. So if I tried every possible move and it did not work out for me, then probably what I want to do is go with +1 to stretch things out as much as possible. Because if I'm losing, then getting closer to actually losing is a bad idea. So I'll just say, you know, I could do it just the once by setting move, but whatever. Make sense? So if it is the user's turn, then we get the input. And we add move to curve position. All right. That's it. So, like, not very complicated. You could, so I tried to write it kind of in a straightforward way. You could compress the logic if you wanted to as well, but I think it kind of makes more sense that way. So now we can play. Or if move in moves, I meant for move and moves. Say that? Line 12. Okay, it's 4. Okay. Thank you. I forgot to switch the user's turn. Okay. Oh, and I didn't print the sum. Okay. So I know how to play it, so I'll say +2. The computer is doing +1, hoping that I'll mess up, but I won't. Amazing. So that's not interesting because it lost, but if I do mess up, wait, why did it move twice? Yeah, but so here I make user's turns false, and here I make user's turn true. Oh, because I do it regardless here, even though that's only if I didn't do that. So what I'll do is I'll say so I'll do like move decision is equal to 1. And then here, this will be like move decision. And this would be move decision. Okay, so that way, regardless, move decision would be either what I decided here, or by default, it's just going to be 1. The problem was before I was doing it twice. So, okay. So now I'll mess up. And now I'm screwed, right? So it doesn't matter what I do. Wait, I won. Hold on. So let's see what the problem is. So here, so we're saying if this leads to win, then I say move decision equals 1, equals move. Make the decision. We say curve position plus equals move decision. Okay, now I'm screwed. Okay. Questions about this? All right. Yeah, so the bug here was I forgot to change move to move decision, but now it's okay. All right. So that's the game. And again, you can make it for anything, right? And this is just the interface. So the big picture is very simple. The big picture is you are trying to find a move that would make it so that you're guaranteed to win. If you find such a move, then you just make the decision be that. All right. Cool. All right. I don't have chocolate for myself. Yeah. Anyway. So, okay. I want to switch to something else for just a second. And that is F strings. So part of it is that tomorrow I'm going to have you work a little bit more with strings. And part of it is like we never got around to doing it. So this is a good idea. And another part of it is there is a cool example that I want to show you that uses this. So this is basically a way of constructing strings that's better than using plus. So before, in order to do something like this, like you could say, like whatever, like ABC plus str2, and you can construct whatever you want like this, but it's kind of awkward. So one thing that you can do is you can do an F string. So this is just a string with the F over here. And that allows you to insert stuff. So for example, my bridge collapsed under how much do you put there? Okay, let's say 12. So you can do something like this. And what happens is whatever is in the curly braces just gets inserted. So you could construct it using pluses, but it would be annoying to do. Here you can just insert whatever and it just inserts it. All right. That's all there is to it. You can use that if you want. You can also use pluses, whatever works. All right. Questions about this? So this ordinarily it would be a variable, but you could also put in any value here. So like if the value is 13, then 13 is going to be substituted. All right. So, okay. The other thing that's really cool about Python and strings is that because, like, if you're new to programming, all you've seen is Python. But if you work with Java, whatever, Java is compiled, Python is not. And that means that you can take a string that's Python code and just execute it. So here's an example. I'll say, here is a string. Name it code. So something like this. So I enclosed it in triple quotes because triple quotes allow me to define strings across multiple lines. For now, it's just the one line. So code is a string like any other, but it happens to be valid Python code. In Python, you can just execute a string by telling Python, treat it as code. The way you do it is with exec. So if you run this, what happens is 13 gets printed. And what happens here is the code was just run. So exec says, take this string, treat it as code, just run it. So it could be as simple as this, but it could be complicated, right? So you could have code that's like this. So that's just like legitimate code, right? And you can execute it. And it'll print 51. So the whole thing is going to run. Make sense? So I'm going to do an example. Part of it is it's kind of fun. Part of it is that we will have the tools to do it the right way, quote unquote, but you don't currently have it. So here's what I want to do. So we've already done that for fixed n, right? So if n is equal to 3, you would say, for C1 in alphabet, for C2 in alphabet, for C3 in alphabet, you print this, right? And if alphabet is like ABC, for what kind of type today? Line 4 for N, sorry, kind of type today. Okay, so that does this. But that's for n equals 3. Suppose I want to input n. I don't want to pre-decide what n is. This technique would not work because, well, I have to type in the nested loop. Except you just saw I can create a string that's code and then run that code. So that's the strategy that I want to use. I want to make a function that generates this code and then run the code. Make sense? So my task here is generate a nested loop of that pen. So essentially what I want to do is I want to build this as a string. All right, let's do that. So, all right, how are we going to proceed? Well, what we want to do is we want to generate it line by line. And then we also need the print. Okay. So we start with code being just nothing. And now I want to add this, and I want to add this, and I want to add this. So I'm going to say, so what do we want here? So we want this, and we also want some indentation. So how much indentation do we want? Well, at first, nothing, then 1, then 2, then 3, and so on. So I'll add empty times I. Right? So initially it will add nothing, and the next time it'll add 1, and the next time it'll add 2, and so on. And then I want to add this thing. So that would be an F string. So I'll say for C I, so this would be C0, C1, C2, and so on in alphabet. And then I want to add a new line. Make sense? So let's see what we have for now. So this returns a string, but if I print it, then the new lines are going to generate nicely. So I get this kind of deal. All right, that's progress. So what's left is to generate this guy. So after I've generated this, I want to generate this. So I want indentation. How many spaces? Well, before I added n-1, so now I want n spaces. So it's going to be indented. And now I want to add print, open parentheses. And now I want C0 plus C1 plus C2 plus C3 and so on. So that's another loop. So I'll add C0, C1, C2, and so on. Actually, I'll go up to n. So I'll add Ci over here. So if we do it like this, then what you'll get is this kind of thing. So we have a plus at the end. So that's a little bit annoying, but that's okay. I'll just add an empty string at the end. So I have like C2 plus empty so that there is no dangling plus. And then I'll close the parentheses. So I'm adding this. This is enclosed and single quotes, so that's fine. And I'll close the parentheses. And they'll do a new line. Don't have to do a new line, but that's okay. So there we are. Make sense? All right. So now what I can do is I can say, okay, so alphabet is whatever, ABC. Can make my code. And that can be now whatever, 8. If I print the code, that looks like this. And the magic thing is I generated the code, put an 8, so I have 8 nested loops. And now I can just execute the code. All right, amazing. So that is like obviously kind of hacky. But and this is not how you would do this particular task. However, the idea that you can generate code and then run it is actually super useful. And it's used, like in advanced settings, not ordinarily in ESC180, but it's a beautiful idea. You can just make a program that writes code, and sometimes it makes your life easier. Two, it is useful sometimes in programming languages, compiler design, stuff like that. Not really something that you should do in real life unless you really know what you're doing, or unless it's tomorrow's lab where it also happens to be useful. One obvious issue here is that if I say exact code and I don't know exactly that the code is fine and I made it and not someone else, well, like it could be anything. So like be careful about that. Sorry. Questions about this? Cool. Let's now do the same thing, but the normal way. By which I mean with recursion. So, okay, how do we do that? So basically, what I need to do here is I need to somehow figure out how to use all strings as its own helper function to help me generate all the strings. So here's an idea. This is not an obvious idea. We are sometimes doing problem solving. So like while getting the idea of I'll just generate some code is like not obvious. Like once you know what you do, this is just like plain problem solving. This is not like that. You have to know what you're doing. So here's an idea of how we are going to go about it. We'll add one more variable, call it start string. And now that's going to become feasible. So this is going to be return a list of all the strings of length n over the alphabet with start str prepended. So the idea is kind of like this. So if you say all strings, and then it starts with X, Y, Z, and then N happens to be 1, and alphabet happens to be 1 to 3. So all strings of length 1 with X, Y, Z prepended. So that would just be X, Y, Z 1, X, Y, Z 2, X, Y, Z 3. Make sense? So everything of length 1 and prepend X, Y, Z, that's a really simple task. Does that make sense? If you say all strings of length 2, then again, X, Y, Z is prepended, but now you need everything that's of length 2. So this would be something like 1, 1, and then you also want 1, 2, and then you also want 1, 3, and then you also want X, Y, Z 2, 1, and X, Y, Z 2, 2, and X, Y, Z 2, 3, and then also X, Y, Z 3, 1, and 3, 2, and 3, 3. Make sense? So that's the task. I made it up, let's say. Right? So now maybe you see how the base case is going to work. What's a good base case here, anyone? Like what's the length of a string that's easiest to generate? Yes. N equals 0. Exactly. That's extremely easy. So if n is equal to 0, so all strings of length 0, that's nothing with start string prepended. So that would be the list that contains start str. Right? So that's even easier than this guy. So if this is 0, then we just return x, y, z. All right. So, okay, let's now do the recursive step. So basically the idea is like this. I have start string. So let's think about this example. So that's what I want eventually. So here's one thing that I can do. I can say, okay, I'll make my life easier by calling all strings as a helper function several times. So I'll say all strings xyz1, and then add another string of length 1 now. And then I'll do the same thing with xyz2, and then I'll do the same thing with xyz3. So that's going to cover it, right? And I'm getting closer to my base case because now it's of length 1. When I call this guy, what's going to happen is I'm going to call all strings xyz 1, 1, and this is 0, so that's the base case. And I'm going to do it with xyz 1, 2, and I'm going to do it with xyz 1, 3, and I'd be done. All right, so that's the intuition. Basically, what we do is we say, call all strings several times, expand the start string, and just call all strings as a helper function. All right. So what do we got to do? Well, we got to go over the alphabet. And add car to the star string and call all strings. So I'm going to say all strings start str plus car and -1 alphabet. Right. So I'm saying initially res is empty. And then I'm going to call all strings as its own helper function. And I'm going to say, okay, like start with this start string and then complete it with n-1 characters. How do you do it? Not my problem. All strings as the helper function. It'll figure it out. Right? So this is kind of like a little bit algebraic, so it's maybe a little bit difficult to get your head around. But this is the example, right? So when we do all strings xyz2, what we're going to do is we're going to collect all the stuff from over here, and then all the stuff from over here, and then all the stuff from over here. That's exactly what we're doing. We started with an empty list, and we're saying extend with this thing, and this thing, and this thing. Make sense? So I would not suggest thinking, okay, like where does it end up? What's going on? Don't think like that. Just think about it in terms of, does it make sense that it should work? If I do start with XYZ1, start with XYZ2, start with XYZ3, complete it with N-1, that's going to do it. Yes. Say it. Why is it extend and not append? That's a great question. So this is a flat list, right? This is a list of strings. I want to return eventually just a list of strings. So I'm just collecting, like get me the strings from over there, get me the strings from over there, get me the strings from over there, and just like put them all together in one flat list. Make sense? All right. Let's see if I managed not to screw things up. So we start with an empty start string. And then let's say 3, and let's say ABC. I did mess it up. So our non-type object is not iterable. Let me do a postmortem. So all string, oh, I forgot to return res. All right. Second attempt, not so bad. I do worse at Wordle. So that did it, right? And like it's kind of remarkable, right? It's like all you need to do is you just say, okay, like how do I call this as its own helper function? You did have to have this idea that you need to add the starting string, which is like not an easy idea. This is a good time to introduce one more piece of syntax. So this is called default arguments. So if you say f, you can say something like this. So this basically says, okay, if you call f without arguments, n will be 42 by default. So f43 will print 43. And just f will print 42. So obviously default arguments can only be at the end of the argument list for obvious reasons. Like if you want to skip the first argument, Python would not know that you want to skip the first argument and not something else. So that is convenient for us because we can rewrite this like so. So I'll copy and paste. So I can say that starting string by default is going to be empty so that when I call all strings initially, I don't have to specify start with nothing. So I would have to change this to be the last one. It's the same. It's just that now I can say all strings, okay, with 3xyz, and I don't have to specify that the starting string is empty. So usually I supply the starting string, but when I don't, that means that it's just going to be empty by default. Make sense? All right. Questions about this? Okay, so so the technical term for doing all strings over the alphabet is all combinations. So on the exam, you'll notice in past exams that there is sometimes a question like that, where you need to do all combinations of something. Sometimes it's strings, sometimes it's something else. So anytime that you want all combinations, what you want is this kind of structure. So the variations would be, it could be like strings. Instead of strings, it could be lists, right? So strings and lists, it so happens that we construct them the same way with a plus. So it's actually not that different. You just change the strings to lists. There's not very many variations of that. Like if you do all combinations, it's got to be something like this. One common type of thing that you see on the exam is do all combinations, like try all possible lists, and then see if there is a list with some particular property or something like that. So that would be, sorry, I don't remember the years, but like several years, I think certainly 2016, I believe 2021 had that as well. So that would be equivalent to find the right password. So to find the right password, what do? You generate all the passwords. Once you have the list of all the possible passwords, you go through the list in order to find the right password or something like that. Make sense? All right. So 2016 last question definitely is that. I believe 2021 as well. All right. So football tomorrow at 6 and also on Friday, if you can do tomorrow, I will announce that on Piazza there's going to be a new sign-up thing. Lab tomorrow, lecture Friday. I'm away at the conference on Tuesday. You'll have class with a TA with like practice thing. I'll be back on Wednesday, and then we have the exam, and then we're done. All right, see ya. Bye.
Is there anything one more time what extend versus a handle?
Yeah, so it's like if you have a list like this, and you have like a list that's like for 5, so L dot extend L1 makes it so that L just has like 4 and 5 also in it. If you append L1, so L is now this, then the last thing that's gonna be an L is actually like a list, right? So what I'm doing here is I'm like collecting all the results from here and all the results from here and all the results from here, and I want to just put them in one list. I don't want like a nested list with lists with lists.
All right, thank you.
Yeah.
On the exam, are you gonna make that's far like make us do like recursion specifically or like the fitness?
I can't tell you what I'm gonna do on the exam.
No, I know, but I'm saying like is that something that's one of in the past?
Yeah. Okay. Yeah.
Thank you.
Yeah.